Kuala Lumpur, capital of Malaysia, home to the world's tallest twin skyscrapers, the Petronas Towers. Supported by the world's deepest foundation, spanned by the world's highest sky bridge. Over $1 billion worth of concrete, steel and glass went into their epic construction that took almost 8 years. The Petronas Towers are not only marvels of engineering, they're uniquely Malaysian icons for the 21st century. Malaysia is a bustling melting pot of races and religions. 25 million Malays, Indians, Chinese and other ethnicities live side by side in a predominantly Islamic society. Economic development between the 1980s and 90s has also put the country on the fast track to becoming one of Southeast Asia's tiger economies. One major beneficiary of this prosperous time is Malaysia's capital city, Kuala Lumpur, the heart of the country's industry and commerce. During this period, the physical landscape of the city transformed. Numerous construction projects emerged, making Kuala Lumpur one of the most built-up capitals in the region.
One of my abiding memories of Kuala Lumpur in the 1990s was just the number of cranes on the skyline. I've never seen a city, I think, with so much construction going on.
But despite the construction boom, the cityscape still didn't have a focal point, a single identifiable landmark that the world would come to know.
Cities, city authorities, politicians everywhere are seeking to put their cities, put their nations on world maps. But it seems to me that perhaps there was a recognition in the 1990s that many people around the world didn't have a clear sense of where Malaysia was.
The Malaysian government sought to rectify this and let the world know they were a true global player. They needed to build a first world icon, grand enough to announce their arrival on the world stage. Taking cues from iconic skyscrapers in the West, the Malaysians decided they would also build a one-of-a-kind skyscraper. Or in this case, two of a kind. They named them the Petronas Towers.
At first, we were all told that this would be the headquarters of the national oil company, Petronas. This building is in Kuala Lumpur. It has to reflect the heritage of this country. It had to reflect the cultures. But very importantly, we said we wanted this building to look beautiful, to show progress.
Alida Arif was one of the key administrators in charge of planning the towers. And, like many of her colleagues at the time, she saw the symbolic value in a skyscraper.
It was very important of us for the symbolic reasons to show progress, to show aspirations of the country, that's aspirations for Malaysia to become an industrialized country. The design of the tower, in particular because of its heights, is sort of reaching for the sky image, seems to depict that aspiration.
The Petronas Towers were supposed to stand out as an ultra-modern icon, but they still had to retain their Malaysian identity and incorporate many of the nation's most identifiable cultural motifs into their design. With this brief in mind, a competition was launched worldwide for top architectural firms to submit design ideas. The winning entry eventually comes from Cesar Pelli, the world-renowned Argentinian architect.
I thought that the request that we connect the building with Malaysia was a very good request. And we explored quite thoroughly Malaysian traditions, Malaysian buildings, Malaysian crafts to capture the essence of what Malaysian means in a building.
Pelly took his inspiration from what he saw all around Kuala Lumpur. He reinterpreted the symmetrical patterns of classic Islamic architecture and integrated them into the design of the ultra-modern Twin Towers. As a result, bridging the gap between technology and tradition. A concept he used to further emphasize the tower's presence as a gateway.
In the brief, we were requested to build 2 towers to form a gateway. Most of the other competitors did towers of varying sizes. But as I was trying to seek a symbolic quality in these towers, I quickly realized that having them in a pair, symmetrically placed, the symbolic value of those towers strongly increased.
With design decided upon, the engineering team was given a deadline of only 3 years to complete the construction of the Petronas Towers. It was an ambitious timeline, and to achieve it, they'd have to build the towers faster than any skyscraper construction anywhere in the world. Even more challenging, the Malaysian builders had no prior experience constructing a super skyscraper. To top it off, one more challenge was thrown to the design and engineering teams.
The question was actually asked by then the Prime Minister, Tun Dr. Mahathir, what would make it the tallest building in the world? And, Pelly thought about it and he said, you probably add another 10 meters or so. And we were struck by the point that that's all that it would take to make it the tallest building, and yes, okay, so make it so.
Suddenly, the Malaysians were not only faced with building a mega skyscraper for the first time, they were also about to construct the world's tallest buildings. Today, Malaysia's capital, Kuala Lumpur, is identified by an iconic landmark, the Petronas Towers. People from all over come to see the world's tallest twin skyscrapers. But as much as the Petronas Towers stand out internationally, they're also able to blend into their Malaysian surroundings. This is the result of a strict brief given to Argentinian architect Cesar Pelli. Pelli's design adapts the geometric shapes of Islamic architecture found all around Kuala Lumpur and reinterprets classical Islamic patterns.
That decorative elements of the towers, floor patterns, wall patterns, that incorporated not only Islamic traditions of the design, but many specifically Malaysian crafts and decorative elements. Those are now transformed into contemporary visions of what is a very old tradition.
Even the shape of the building has its roots in Islamic design. 2 interlocking squares form the 8-pointed star shape of the tower's floor plate, an important motif in Islamic art that symbolizes unity and strength.
This interlocking of the squares have played very importantly in the formed floor plate of the tower. Now it's based on a simple geometric form of a square, okay, and interlocked with a second square, and this forms the basic geometric form of Islamic geometry.
But the floor plate design has a fundamental problem. Its interlocking squares limit the usable floor space in the building. A solution is quickly found.
We slowly changed it by adding 8 semicircular lobes into a 16th lobed star. This is now a very efficient floor plate.
To explain this further, Cesar proposed that at the intersections of these squares, he proposed circulars, and that's how the floor plate got projected out, and we have a sharp edge, a rounded edge, a sharp corner, a rounded corner.
The major design issues may have been resolved, but the bigger challenge remained. How do you build the tallest skyscrapers in the world? Back in the 1990s, the country's tallest building was a mere 60 stories. Constructing a skyscraper at a record-breaking 88 stories would be a tall order for Malaysia. There was a lack of experts with the depth of experience needed for a project of this scale. A multinational team was quickly assembled, the likes of which had never been seen in Malaysia before.
This was very much a multinational effort. We had the English, we had the Scots, we had the Americans, we had the Canadians, we had the Japanese, we had the Koreans, we had the Chinese. You know, almost every single country was represented in one form or another. So it wasn't just a local effort.
The engineer's first task is to figure out what material to build the Petronas towers with. Skyscrapers are usually built with steel, but steel is not only an expensive material, it's something Malaysia is short of and also unfamiliar with.
Now, if these towers were constructed in America or in Japan, they definitely would have been steel structures.
To build the towers this tall, using mostly steel, would have blown the budget sky high. The solution was to go with the one material the Malaysian construction industry had in abundance: concrete. Chris Landry is a concrete supplier who knows very well what the challenges are with using this material.
The Twin Towers took approximately 180,000 metres of concrete. That's a fair volume of concrete in any structure. Every metre of concrete uses approximately 2 tonne of material, and we were pouring 24 hours a day, so you can just imagine the volume of material that was going through the actual site.
Concrete, the world's most common construction material. A building made of it can resist strong winds and absorb twice as much vibration as that of steel. But concrete isn't as light as steel. Using it would make the Petronas towers the heaviest structure on Malaysian soil. The combined weight of the towers reaches a staggering 600,000 metric tons, the equivalent of almost 4,000 jumbo jets. Needless to say, their tremendous weight also meant tremendous pressure on the ground beneath.
We are talking about loads, mega loads. Here we have each tower's loads which are close to about 300,000 metric tons. So under such loads, with such mega building, we would need a huge and a large foundation to carry this building.
To cope with the crushing pressure generated by the weight of the tallest towers in the world, engineers realized they'd have to plan and build the world's deepest foundation. Kuala Lumpur sits in the Klang Valley, a flat alluvial land surrounded by limestone hills. But while the valley's floor appears to be a smooth and unchallenging landscape, what's underneath can be as erratic as the limestone outcrops that encircle it. Building the world's deepest foundation on such unpredictable ground would be easier said than done. Before building the massive foundation, the geotechnical profile of soil conditions at the site will have to be studied. This involves drilling over 400 exploratory boreholes into the earth. Stephen Tong was the structural engineer on the ground whose task was to examine the test results. To his dismay, his worst fears came true.
The location sits on the edge of a cliff. Being a tower of this height, you know that the stresses underneath the soil are tremendous, and sitting on a cliff means that it causes tilt on the tower.
The underground cliff that the towers are to sit on is limestone bedrock that starts shallow but slopes steeply downwards, more than 180 meters.
Normally, limestone is good soil and it's rock. It provides a good end bearing for foundation. But in this case, the limestones have cavities in it, and that poses a soil problem.
Over time, the problematic limestone bedrock can result in unevenness and cause the towers to tilt dangerously. The engineers broaden their investigation around the site. They discover stable terrain 60 meters away from the original location. By moving the site to the new location, the towers avoid problematic bedrock and anchor firmly on stable soil. A massive concrete raft will now be constructed and laid across steel pilings, drilled some 125 meters into the ground.
The foundation system of these buildings is actually a combination of pile raft foundation. Piling meaning deep columns penetrating into the soil, and the raft capping all these columns.
To prepare the ground for the foundation, an army of builders and digging machines are brought in to excavate the initial depth. Even a large underground stream is no match for these diggers. Powerful water pumps are used to turn the stream into a mere puddle. Pilings are driven firmly into the ground to form the skeleton of the foundation. To fill the 4.5 meter thick foundation skeleton, over 13,000 cubic meters of concrete is required, the same volume as 5 Olympic-sized swimming pools. The quick-drying nature of concrete meant that any delay could ruin the entire pour. So the team sets a punishing pace, pouring an average of 1 truckload of concrete every single minute. The pouring goes like clockwork from day to night. Not even a strong tropical storm can stop the men from continuing their work. After 1 year of planning and building, the massive foundation was finally ready to support the heavy loads of the Petronas towers. There's no time to waste. Engineers had just 2 years left to build the towers that would become the tallest skyscrapers in the world. There would be no room for mistakes. Among the most distinctive features of the Petronas towers are the pinnacles. Twin spires that form the apex of Kuala Lumpur's famous landmark. They stand 452 meters above the Earth's surface, crowning the world's tallest twin towers.
The idea of wanting to have the form of the building extend itself as much as you can into the sky, I think it's a basic human impulse. It's the desire, perhaps, of trying to connect our earthly beings with something higher in the sky.
Today, the Petronas towers provide an effortless view of the Kuala Lumpur landscape. But 10 years ago, taking the towers to their record-breaking height was not so easy. During the construction of the towers, building each floor of the 88-story skyscraper was back-breaking work with no margin for error. As the Petronas towers began to take shape, engineers had to maintain the tower's verticality. This means keeping the building straight as it climbs to the top. A deviation of even millimeters can cause the skyscraper to lean. Building crews were also in the race against time. They had only 2 years to complete the construction of both towers. To meet this tight deadline, planning managers realized they had to build one floor of the Petronas towers every 4 days.
We were looking at a 4-day cycle per floor, and that is very, very fast. Even today, that is still among the highest rate of construction in any of the tall buildings anywhere around the world.
To maintain the rapid 4-day cycle without compromising the integrity of the structure, engineers decide to use concrete. Besides its strength, builders in Malaysia were more familiar with concrete and worked faster with it. But using ordinary concrete to construct tower columns 452 meters high would result in massive column sizes and affect the building's design. So high-strength, more compact concrete was needed to streamline the columns. The problem was, this type of concrete had never been used in Malaysia before. Engineers brought in high-strength concrete experts, like Simon Jeffrey, to push the concrete mix to unprecedented strength levels.
Here's our compression machine. This machine can compress up to 3,000 kilonewtons. When we're dealing with skyscrapers, we have zero margin for error. How we guard against it, our primary guard is we over-design our mix. For example, the grade 80 that we supplied to the towers, the average strength achieved was 101 megapascals. That's 25% stronger than what the engineers stipulated.
The grade 80 high-strength concrete is so strong, it's able to withstand the combined weight of 500 elephants for every square foot. The engineers were now not only able to build really fast, but also create a concrete monolith stronger than most skyscrapers. But the outer cosmetic beauty of a skyscraper is just as important as its inner strength. Besides trying to build the tallest skyscrapers in the world, the Malaysians wanted to build one of the most beautiful buildings in the world. But beautifying giant skyscrapers is no easy task. It would involve using over 80,000 square meters of steel to add another unique feature to the towers.
These are the only 2 towers in the world which are cladded in stainless steel, completely. The stainless steel is a beautiful material.